Thank you very much. Hello everyone. Since this is the last talk, let me just share an observation. I like how many of our plenary talks actually connect to each other a bit. Sometimes it almost seems like there's a narrative going on, like designed one. There is no designed narrative, but there are connections. Like we heard before, like Pas2.js and FPC WebAssembly. Yeah, I will mention them too. They also connect to what I'm doing. So that's kind of great that all of our talks. There are a number of threads, yeah, that go through many of them. Hello, I will be talking about developing games and graphic visualizations in Pascal. That's a long way of saying that the only thing I know how to do in my life is to make a game engine, and I guess I've been doing this for a long time. So I'm Michalis Kamburelis. I'm the author of Apus Game Engine. Thankfully, not the only developer right now. We have a lot of contributors, so I'm happy about it. I'm also currently the maintainer of PasDoc, which is a documentation generator for Pascal code, completely independent from Apus Game Engine. It scans your Pascal code, Delphi, F3 Pascal, and generates HTML or some other formats documentation. I also wrote something called Modern Object Pascal Introduction for developers, for programmers. Go ahead and check it out. I'm not sure if this introduction is a book or if it's just a really, really long web page that you can download as a PDF too. But it has been written like with the desire to give a concise overview of Pascal, especially for people that come with maybe some pre-existing knowledge about maybe other programming languages, but now they'd like to see how it all works in Pascal. So it tries to explain some, let's say, advanced, at least, okay, non-trivial topics in Pascal, and I hope it succeeds because it has a lot of views. This one thing, Modern Object Pascal Introduction, has much more visits than the engine and everything else I did in my life. So I guess it works. Some other things that I'm doing, aside from Pascal stuff, is I'm Web3D member and the liaison between Kronos and Web3D Consortium. That's a lot of words, but the short version is that I participate, maybe I even did something in some standards, about the standards for 3D models. So how do we interchange 3D models between applications? Of course, I have a vested interest in it as a Apus Game Engine developer, but this is something that basically how do a lot of software can interoperate to create 3D models. I will mention it today because it does connect a lot to what I'm doing. Finally, I'm also the co-owner of Catastrophe Games. It's a Polish indie game development studio. We develop games, some of them also in Apus Game Engine, and I did not want to spend so much time actually on this slide, so sorry. Everything else is more important here than me. All right, so why this talk? That's how we did the graphics long time ago, right? The graph unit and draw and fill and so on with colors. And basically, that's what we kind of can do today. So those are the screenshots, 2 screenshots from my engine. The design time of creating a 3-dimensional world. On the left, you have this hierarchy. On the right, you have this object property, object inspector. And on the right, there's a running game, okay? So that's the purpose of developing all those things, to be able to create some impressive graphics, impressive game engine that allows you to have fun logic and allows you to create modern games, all right? So the first part of this talk is I'm going to talk about modern graphic APIs. This one is not really related to Pascal, but I hope it will actually give you a good overview of how all those things work. I will not go too much into details, but just I think to give you some overview if you'd like to develop, for example, your own engine, which really don't. It's like, you will lose your life. But if you would like to, I will give you some pointers, I guess, how to do it. Okay, so what do I mean by modern graphic APIs? Well, I mean OpenGL, but let's expand the definition. So first of all, we do want to work with 3-dimensional objects. And they are getting like higher poly. I mean, you can load to the open GPU more and more vertices, and it will handle them. The modern GPUs can handle loads, millions of vertices, like if you load them efficiently, and they can render them. So 3D and 2D too. And 2D is a special case of 3D. Yeah. Okay. So this wall is 3D. It's also 2D. You can provide textures for everything to provide additional details, not just for the colors, but also, for example, how the lighting interacts with a surface in interesting ways. And then there are shaders. Shaders are programs that you load on the GPU. And the GPU is a graphic processing unit. So shaders are programs that you load on the GPU and that tell the GPU what it should do about all those vertices, pixels, and what colors to display ultimately. And I will show actually an example of shaders. That's one of my points of this section of the talk. And of course, we want to utilize our hardware. Yeah? GPUs are fast. GPUs have modern hardware support for all of this. We want to utilize this. All right. So a very short overview, how does rendering on GPU work? This is short, but actually good overview. So it starts with an input, right? So imagine that you have a box. A box is 8 vertices, 8 corners, and the box has 6 sides. Each side is a square, and the square is 2 triangles, okay? So you have 8 vertices and 12 triangles, and that's your input, okay? What does the GPU do? Well, it really does 3 things, one after another. First of all, it processes each vertex. So you have a box that has 8 vertices. Each of those 8 vertices in a 3-dimensional world, it will be mapped to screen. Okay? That's the first part of the job. You can customize how it's done using the vertex shader. Then the second part of the job is rasterization. So now you have 3 points on your screen where the points of your triangle are. Okay, but now you have to fill this triangle. And that's rasterization. And the final step is, okay, once I have determined what pixels to draw on my screen, I have to also determine, what colors should they have. And that's the job that is done per pixel. And it's called fragment shader. For our purposes, fragment and shader are the same words for this hour, all right? Now, parallelism, this one, for example, connects to our threads. So why is the GPU so fast? Because everything I explained on the last slide, I mean, not everything, but a lot of those things can be done parallel. So for example, you have a lot of vertices. Yeah? The cube has 8, but your models will have millions, okay? And basically all this processing of vertices, it's independent of each other. So you can do that all at once, at least as much vertex processing units as you have. And then once you have any 3 vertices that form a triangle, you can rasterize it. So again, some piece of the hardware is doing more vertex processing, the other piece of the hardware is doing rasterization. And once you have a set of pixels to draw, then another piece of the hardware is taking care of drawing each pixel. And again, each pixel is kind of independent. That's a simplification. There are actually some requirements in what order to draw the triangles, but that's good enough. Yeah? So all of those boxes, vertically and horizontally, they execute in parallel, and they process a lot of data this way. All right. And now shaders. This is the one that I want to emphasize to you as a practical thing. So shader language is a specialized language that you can compile and then execute on the GPU. It's very specialized. You will see an example of its syntax in a second, 10 seconds. 2 examples that are active nowadays are OpenGL shading language, that's the one I will be showing, and the HLSL, which is used in Direct 3D and some other software that maybe is or not Direct 3D. Okay, it's Unity. Okay. Shader languages have operations that work fast on vectors and matrices. And what it means is, for example, what's a vector? It's a position on 3-dimensional world, or it's a color. So those are the things we care about when we render stuff. And shader languages have excellent support to do calculations on them. The shader language doesn't have any I/O. You cannot write under anything. You cannot debug log there anything. There are no strings. There's not even any recursion allowed, not indirectly, which is interesting property because it means that actually you can, in terms of Pascal, you can think that actually every procedure function in GLSL, it can be inlined. And at the end it is actually, from what I know on all the available hardware. At the end, there are no function calls in GLSL. It's all inline. It's all a giant block of code once it's, compiled to something more or less intermediate. All right. So each shader has a number of general parameters, like a material color. Vertex shader as an input gets a position of all those vertices, and it outputs a position of those vertices mapped to the screen. Well, that's a short description. Fragment shader processes what it gets from the vertex shader, for example, texture, and it outputs the proper color of this vertex. And now let's actually get more practical, okay? So I wanted to propose to you a way to actually test writing shaders yourself, because it's very easy. So I'm going to use an example, shaders inline. It's an example written in the X3D 3D model format. but you don't care about it. Your way of thinking about it right now should be, it's a text file. It's a text file that contains a vertex shader and a fragment shader. And I can easily display this text file using something called View 3D Scene, which is a Pascal Game Engine tool that you can, of course, download for free, of course, and so on and so on. So let's experiment with it. So this is the X3D file that defines shader. Is this, you see it? Okay, the contrast, everything? Okay, hopefully that's okay. So this is the practical, what is the vertex shader, okay? So it gets a bunch of parameters, it gets some input like texture coordinate, and it's processing them. There's really one important line here, this line that says, take the castle vertex, which is the three-dimensional vertex on input, multiply it by some matrices. If you don't know what could it mean, the multiplication by matrices, it will be problem. Don't worry, basically, but it's fun. And it's also not that complicated. It's a way to transform one vector into another vector. And then the output is a position of the vector on your screen, okay? So that's a vertex shader. And now what we have below is a fragment shader. And this fragment shader is really simple. It says, take the texture pixel that I should display at this point, and use this texture color as my as the color that I should display on the screen. The GL underscore frag color variable here is it's kind of magic. Maybe it's sometimes not. Never mind. It is kind of magic here. It determines what color will be displayed on the screen. And it works, and I'm showing you this simple demo to kind of also encourage you to experiment with shaders this way, because it's so easy. So what we do below the one, so we actually use this shader for a sphere shape, for box shape, for cone shape. So all of those things are like Pascal Game Engine in this case is feeding the GPU with the data about vertexes and about texture coordinates. And what you do, you write shader, which means how to deal with this data to display whatever you want. And now just to show some power of the shading languages, what can we do? Well, for example, we can process those colors, yeah? So like, for example, negate the red color, yeah? So this is it, yeah? glFragColor.R for red, and then negate it. So -1 minus red, and yeah, it's as simple as that. You can just try it. So we can reopen it, and now the colors have changed. I hope it's also visible it on this projector. They did change. The red is different. Yeah. So you can do a lot of interesting things. For example, maybe we can zero the green and blue channels. Okay, and this will be definitely visible. Yeah. So now only the red channel remains, and maybe we want to apply something like. Let's call it the most naive implementation of increasing the contrast. So we bump the input to some power, and this is effectively like increasing the contrast. That's a very simple way of increasing the contrast of your image, okay? And that's what we can do with shaders. So that's a very simple framework that I want to propose to you to play with, how to use the shaders. I think it's kind of effective. This is the graph of this very simple power function. And yeah, everything that you will see, everything that is rendered by Pascal Game Engine or any other game engine or 3D visualization engine, everything goes through this code or similar code, but it's a shader everywhere for everything right now. There are more utilities for shaders, like geometry shaders that can generate primitives and compute shaders that can perform arbitrary work on the GPU. I will not go into details here because I want to go to Pascal, so I don't have time to do everything, to tell you everything I would like to. OpenGL essentially then is basically load your data to the GPU, like vertex positions, load your textures, load your shaders, and then each frame display them. Display them using something we call drawCall, which is a command to the OpenGL to actually do drawing of some shape. And then beyond OpenGL, so we have something like OpenGL ES, for example, which is basically an OpenGL that runs on mobile devices. We have WebGL, which is basically OpenGL from JavaScript, and you can use it in the browser. And then there's Vulkan. Vulkan is a new API from Kronos. It's much more low level than OpenGL. It needs much more work to render anything, and then even more work to actually get this extra speed that you have been probably promised when somebody enticed you to implement a Vulkan implementation. But yeah, if you will go this extra mile and implement a Vulkan renderer in your engine or particular game, you can get amazing performance. Why? Because Vulkan matches much better what the GPUs are doing. So if you want, there can be much less like level of abstraction between your code, what you want, and what the GPU wants you to deliver. And then Vulkan is very friendly for splitting the work into threads. It doesn't mean that the Vulkan is a thread-safe library. It is not. You have to be super careful and read the documentation of Vulkan that in this specific situation, this one function can be called from multiple threads as long as it's using different resources and so on. So it's not easy to utilize this, but yeah, it's worth it, right? With OpenGL, you have to essentially do all your rendering in one thread. Sounds some trick, but that's for later. With Vulkan, you can really spread your work into multiple threads. They can be all equally put to work, yeah, to do something. So Vulkan allows you to use all those threads that you are also hearing on our other talks and workshops. And yeah, you can use those threads to actually put work on GPU with Vulkan. That's possible. Hard, but possible. Okay. And there's something like WebGPU. It's basically like Vulkan, but in a browser, a bit of WebGL counterpart. Okay. Okay, let's jump to Pascal, because I talk too much about things that are not Pascal, maybe. So what is the easiest way, I guess, to experiment with OpenGL? And the easiest way is I would advise you to use Lazarus LCL-T OpenGL control. It's trivial. Drop it on a form. It has an OpenGL context initialized, and you just write a bunch of code what to execute for OpenGL. All right. So if you want to like go with OpenGL, like the low level, that's the simplest thing you can do. All right. Yeah. In a browser, yeah, we talked so much about WebGL, and yeah, WebGL is available in a browser. WebGL is available for JavaScript developers in a browser. And so we can use WebGL from the Pas2.js. So we can use this Pascal to JavaScript transpiler to write a Pascal code that utilizes WebGL, which means that what the video that I'm showing, I actually don't show it here, but this one is running in a browser. It's a screenshot of a window of a browser. This is running in a browser. This is rendering some infinite terrain in a browser. And yeah, so there are examples how to do it. Go ahead and use them. There are more examples how to use basically directly OpenGL context from Delphi or from Lazarus. It all comes down to initializing the OpenGL context, maybe using some high-level library, maybe using some operating system-specific library, and in the end, you just use OpenGL commands. And again, there's lots of literature about it. We have a number of OpenGL bindings, which means Pascal units that define OpenGL headers, like there's a Sasha Williams OpenGL header. There's a specific headers built into FreePascal, some headers built into Delphi. The one header for OpenGL that I'm really excited about is glad. It's a framework for generating automatically OpenGL headers for a number of programming languages. And the glad version 1 actually supports Pascal. So I can go to this thing, I can say, I want Pascal. Or maybe you want something else. I want Pascal, and I want Pascal for OpenGL version 4.6, so the latest one. And maybe I'll even throw some extensions, okay? And generate for me a header, which is a Pascal unit that I can use to access all those functions, okay? So, ta-da, can I download it directly? Yeah. Will it open in something reasonable? Yeah, so that's it. That's the header generated that contains all of those definitions of OpenGL constants and then OpenGL function, and it will initialize them. What's the benefit of using such generator? The benefit is that there's no maintenance needed when the new version of OpenGL arrives. Oops. So, and it happens, yeah? When the new version of OpenGL arrives, if you have the manual header, then somebody has to do some very boring work to update it to the latest OpenGL version. With glad that's not necessary. So I'm excited about actually this approach. There's something called glad version 2 that doesn't support Pascal yet. If you're interested, help me make it also use Pascal. All right. Oh, and the glad also uses Vulkan. Yeah. So if you get this, if we port glad 2 to Pascal, And it should be just a matter of defining a few template files. It's really easy, I think. I didn't do it, so it seems easy. So if we do it, we also get headers for Vulkan. So we get headers for OpenGL, for Vulkan, for all the foreseeable future, because this generator as an input is using XML or I think XML or JSON files delivered by Kronos. So when Kronos is making a new version of OpenGL or Vulkan, they deliver the input to the generator, and then you just run it and you get a new unit that has everything you need. All right, let's jump into maybe the most important part of this presentation. So Pascal high-level drawing libraries. So high-level, it means that they hide from you this OpenGL or Vulkan that I was talking about. So this will be like a presentation of a number of things, okay? Some of them I'm deeply familiar with, some of them I'm not, but I know that they are terribly important. Like Skia, yeah? We heard today, both Delphi and Pascal are heavily focused on Skia. So I guess Pascal will be like, we have a dependency on Skia very, very soon. And maybe that's cool. Yeah, Skia is developed by Google. It has a lot of cool features. And it's a library, basically, if you want to have a pretty UI with some fancy effects, like particle effects. Yeah, from what I understand, that's almost a given. It's literally a given, yeah? And then it can also be your like, rendering workhorse to render anything else you want. You are limited to 2D. I'm guessing there are some ways to overcome this, but you are limited to 2D in Skia, basically. But yeah, if you want to render 2D with some effects, that's your way to go. I will talk over this video and I will not let it finish, actually, because I'm ashamed my knowledge about Skia is not as good as I'd like to be. I came here and then I heard I have to learn Skia because everybody seems to be using Skia. So that's a great thing, and well, it seems to be a great library. I want to learn about it more, and I guess you should too, because as I say, it looks like soon it will be like this big dependency. Yes, the Pascal will not exist without Skia. Maybe that's what should happen. All right. Next thing is a Firemonkey 3D. That's something built in Delphi. It has been built in Delphi since the adoption of Firemonkey in Delphi. It has a number of useful features, and I guess the biggest benefit is that it's just there. Yeah? You can just create a three-dimensional context in Delphi with Firemonkey 3D, and it's just there. Yeah? You can put their models, camera, materials. It works. There are a number of things that I could say maybe are missing in terms of performance or support for some specific model formats, but you can overcome this. Internet has actually a lot of documentation about how to extend Firemonkey 3D with something you may want. For example, there is this nice library FMEX, the E stands for the extended, from Vincent Giselle, and for example, it has a loader for the very popular OBJ format. Yeah, it's not. There are other formats, maybe ones I would even advance more, but yeah, it's a popular format, and so you can extend Firemonkey with code, and I guess that's a big advantage of Firemonkey. Yeah? It's there if you use Delphi. It's just already there, and you have loads of documentation on the internet how to extend it. And now we jump finally into something I know, because so far I've been faking it, okay? So something I know is Pascal Game Engines. And the first one is mine, but okay? I'm also going to talk a lot actually about not mine. So Pascal Game Engine is an open source game engine, not framework, game engine, period, okay? It supports 3-dimensional and 2-dimensional games, and I guess the big two features for us is, first of all, you have the editor to visually design your stuff. 3-dimensional games, 2-dimensional games, some UI specific to Pascal Game Engine, UI that is customizable. Yeah? When you open a game, when you run a game, you actually don't want the game to look native to your Windows or Linux. You want the game to be styled, debbed, so that it looks science fiction or fantasy. Yeah? You want the UI to be styled, and that's why we have our own UI that can be styled this way. It can be scaled, UI scaled in a way similar, for example, to Unity. So we have various good things about it, I think. And then our second feature is, well, surprise, surprise, we have an object-oriented Pascal code, object-oriented API that allows you to, to do everything you would like to. You can do everything in Pascal code, you can do everything that you can also design in the editor. And a lot more, of course. And we do follow, well, quite obviously, what Delphi and Lazarus visual form designing is also exposing to you. So everything you put on your scene, well, that's a Pascal class. And it has a bunch of properties. You see them in the object inspector. Well, those properties are Pascal properties. So like when you learn to use the editor, you also learn how to code. That's a very powerful thing. You all know it works. It also works in Game Engine. All right, now I have a short video that actually explains how to use the editor. I recorded it because otherwise I knew that, well, I would make some mistake. Give me a sec. Oh, yeah. Okay, so that's our Castle Game Engine editor. And here I'm creating a new project. I will try to talk over this example, okay? So initially the Castle Game Engine project, this Castle Game Engine project has a number of views. And what you see here is a three-dimensional world that contains a few scenes. I can explore the data in my project. I can render various animations. I can explore the model of the level or the model of the enemy. And I can look around at design time. I can look around closely. I can focus on something specific. I can delete stuff. I can delete stuff from my design, of course, easily. I can add stuff to my design by dragging and dropping. I can duplicate stuff. I can multiple select and edit stuff. For example, to change the animation of it, that's using the glTF animation system underneath. Things have a camera. The world has a camera that determines what the user, if you will actually run this application, what the user will see. Well, user will see what the camera shows right now. The camera preview is shown in the right bottom corner, and I can modify the camera. I can modify it from the editor, and of course I can modify it from code at runtime. So every 100% things that I'm showing here, including creating and deleting, everything can be also done from code at runtime. Here I'm playing around with actually changing the class of the light. Okay, this one needs to do some tricks at runtime. But here I'm changing the class of the light to something else. It was a directional light, like a sun at an infinite direction from the thing that it lit. And now it's a spotlight, so it's like, it shines along a cone. It's probably actually more or less obvious here. Here I'm changing the color of the spotlight to blue. No idea why. I wanted to show this dialog, I think. And what did I do more? Aha, and now let's play with physics. We are integrated with a physics engine, Kraft physics engine from Benjamin Rousseau. I will talk about it more in a bit. And the physics means that you have objects can have something like colliders and rigid bodies. And that means that when the gravity works and when something pushes something else, then the collisions are resolved. And the physics engine tells you what happens when the objects fall down, what happens when they collide with each other. Maybe one of them will push another. Maybe one of them will fall down from something or into infinity. Basically, interesting things happen. What I've been doing here, I've been adding colliders and rigid body information to this level. Here I also dragged the enemy to be in the air because it happened. Let's let it go. And now I'm going to run the physics simulation from the editor and observe the results. That's always fun, always something unexpected happens. And of course, I'm running here the physics simulation from the editor. But you could also, at runtime, you would also see the same thing happening. Finally, you can also drop, like you don't have to use the three-dimensional models for everything. For example, we have a support for sprite sheets, and here we have also support for images, traditional images, which sometimes makes sense to just put an image like on your level. And this is a simple image. What I'm showing you right now is that I can attach to it a billboard behavior. So if you know Unity, for example, Unity has this thing called components, and in particular, mono behavior. Our equivalent of it is castle behavior, and yeah, the idea is that you have something that is rendered, that has some position, and behavior allows to change it, to maybe show something else, to update it constantly. In this case, what you saw is I added the billboard, which means that the image, it was a flat two-dimensional image, but it was always rotated to face me. I didn't even manage to catch up with the video, right? I'm so fast, and this was I didn't speed up this video. So I guess I hope that was fun, okay. Okay, and that's, I guess, a simple hello world from code. You usually don't actually write the application this way. You usually actually place your code in events of a view, which is kind of similar to how you place in Delphi and Lazarus forms events, code inside the events on your form. But here, this is like a very simple Castle Game Engine, like hello world application. This is everything you need to display a three-dimensional model with lighting, with some examine, navigation, interactivity, with possible animations. Yeah, and it works, okay? So we open a window, an area on our screen to actually render anything. Then we open a viewport, which actually can limit the area where we render things. In this case, it doesn't limit. In this case, I'm just using the viewport full size. We place camera, we add some navigation so we can look around, we add some light to actually shine on the model, and then we load a scene. And the scene in this case is just a glTF model. It's a file. It's a glTF file generated from Blender. No, actually, in this case, it's downloaded from Sketchfab. And yeah, and you add this file to your scene, you display it, and you're done. Okay, so, and I hope you see it. Yeah? That's a cat with a jetpack. It's actually a cool model that I like. All right, so some more about Castle Game Engine features. So we support Pascal and Delphi, sure. We support a number of asset formats. I think I talked about this already, but we support glTF, X3D. We have great integration with Blender and Maya and 3ds Max and everything else that supports glTF. That's the bit about me liking 3D standards comes in, right? So I like those standards, and that's the benefit, yeah? We basically support any authoring tool you like because they probably support some format that we handle, like glTF. We have a number of graphic effects, shaders, mirrors, shadows, physical-based rendering, bump mapping. I just read them from the slides very fast. Go ahead and check out the website for the details how to use them. And I guess the thing I want to emphasize will also like friendly to continuous integration, which is something that may be sometimes overlooked in the game development community. So if you'd like to use GitHub Actions, GitLab Continuous Integration, Jenkins, if you'd like to put this stuff into Docker or command line application, you can all do it using Castle Game Engine tools. It's kind of trivial, it's also documented. We have a clear documentation how you can add GitHub Actions support, for example, into your project, and we are actually going to do it on the last part of the Castle Game Engine course later today. All right, we also cross-platform, and the big thing for us is that we cross-platform in terms of where your target is, so where your game can be played, and we also support a number of platforms as like a source platforms, so where you can actually run the editor and design your game. So you can run the Castle Game Engine editor on Windows, Linux, macOS, FreeBSD, and Raspberry Pi. Even there, you can just run the Castle Game Engine editor, even on Raspberry Pi. I mean, you can run the Castle Game Engine editor. It's a native Raspberry Pi application. You can design your games on this amazing, small, fantastic device. And then we support mobile, we support consoles, which means Nintendo Switch. Right now, I'm actually thinking about Xbox. I have the Xbox development kit. I could do it someday, I will. But I guess the most important target that I'm thinking about for the future is web. Is web using FPC WebAssembly target. We've already managed to recompile actually the Castle Game Engine for the WebAssembly target. Well, the compilation is the first step, okay? Getting it to work is another, probably longer step, okay? But we did this first step, and we definitely want to focus on it this year, actually, to hopefully get a working web target in Castle Game Engine. The point is to basically allow you to deploy any game you have into web. And it means it's deployed into a JavaScript and WebAssembly file, and you can just display it in a browser, and people can play it without downloading anything or agreeing to anything for that matter. It's the basic rendering doesn't require permissions. We've made games released on Steam, Nintendo Switch, Android, iOS. That's also important for your cross-platform support. Here I would like to show one game developed by our Catastrophe Games company, and then yeah, it's been the game that I was designing when my wife was pregnant actually, and I think it shows in some of the designs of the games. So that's an Unholy Society game. It's using two-dimensional graphics done in Spine. Animations are done in Spine. It has a light-hearted humor from religion. I think nobody got offended, but it's a humorous approach to exorcism and other stuff. And there's a fun story behind it. And the point of this presentation is that, well, you can develop two-dimensional games with, I think, quite cool graphics, with professional artists also. And yeah, they look good, and professional artists, they said to me that the engine, no, actually they said that the engine sucks, but then I fixed it, and now they tell me that it's good. Okay, so that was my input from them. It was more nuanced, I'm kidding, but yeah, I got the feedback from the people who know many game engines, including Unity, and yeah, we work actually together to actually, yeah, be competitive. In some small way we are. Castle Game Engine, as is the last slide about my stuff. Castle Game Engine is no longer a solo project. I'm so happy about it. We have a number of contributors. I also have one contributor that is like, I pay him specifically for the Castle Game Engine features. We have some people in our company also, we're just using this engine. So I'm happy it's no longer a solo project. I'm happy we have so many contributors. We are looking for the community support. That's on Patreon. We are also looking with cooperation with companies. If anybody here like sees a venue for some cooperation, like maybe you want to have a consulting, you want to use this Castle Game Engine to do something maybe non-standard, you'd like to get some consulting or features or platforms, talk to me. All right, that's enough. I will get back to this, my engine, but that's enough for a second, all right? So let's move on to projects from other people. Benjamin Rousseau, a short version BeRo, he goes by this alias on the internet. He made a number of useful things that can be used in game engines. In particular, there's Kraft. Kraft is a physics engine. It's a very nice physics engine developed completely in Pascal. I actually already told what's a physics engine over one of the previous videos, yeah? So physics engine, it means that you define a number of rigid bodies, and rigid means what it actually means in English, yeah? So the word, something that cannot be squished. It's rigid, yeah? So when it falls down, I guess, it falls down, it bounces, okay? And then those things, they collide with each other. And something can push them, like you can define a force that pushes them, and then something, and I mean the physics engine, resolves the interactions, which means that it tells us where the objects should go, how should they rotate. And so I told about it. Kraft is a physics engine implemented in Pascal. Here you have the Benjamin Rousseau Patreon and the URL to this project. And yeah, I kind of exploited it because I used it in Castle Game Engine, of course, with his knowledge and with the permission of the license. It's amazing. I mean, it works. It's the underlying workhorse of this physics that I was showing you a few minutes ago. And actually, then I have a demo. So I'm sneaky, right? I'm talking about Kraft. I'm also still talking about Castle Game Engine. I can never stop. But this demo is showing Castle Game Engine using Kraft underneath to perform the physics simulation. So that's a two-dimensional case of the physics simulation. So all those balls, all those squares that fall down, and this plane that I'm moving, I started with some desire to make some game, but it was, in the end, it was just fun. So two-dimensional physics simulation works. It's a lot of fun, as you saw. And the next demo I'm going to show here is a three-dimensional physics simulation. You can probably guess what it is. Yeah? So I'm walking around on the level, I'm shooting with some objects, and those objects are simulated using physics. So I'm not like, when I shoot, I don't know where they will hit. I just place, before my eyes, I place this bullet. And then I say, physics engine, calculate what should happen. And it does calculate what should happen. It flies, maybe it hits a floor, falls down. And I destroyed some boxes, some pile of boxes. I created more boxes and I will destroy them too. Yeah. So that's a lot of fun. Physics engine is always a lot of fun because unexpected things happen from the simplest interactions. It works in games, and yeah, that's why we support it. Finally, we support Kraft has, and we use it, we support something called joints. Joints means that in the real world, the rigid bodies are sometimes connected with each other. For example, using hinges or using glue or something like this. How am I with time, actually, by the way? Okay, not terribly bad, I think. All right. So I will speak faster, if that's all right with you. No, I will try to restrain myself. All right. So joints mean that some objects are connected with each other, like in reality. And this means that I can create things that look like, they are tied on a rope to each other, or they are tied with something else to each other. And it works really nicely. All right. What's the next thing I'd like to show? Okay, this will be fun. The next thing that Benjamin Rousseau implemented, he implemented a lot of things really, and it's amazing to actually look at what he's doing. He implemented a networking library dedicated for real-time games. It's great for making multiplayer games. Like think about Quake, all right? And it works. It uses the UDP protocol, but it's made to be actually reliable with the UDP protocol. Well, reliable to the extent that you require reliability, okay? So the reliability, yeah, I managed. Reliability is configurable there in this library, which allows you to trade the speed versus, well, maybe the guarantee that you get something. And it's open source by Benjamin Rousseau, and I'm going to do the same trick I did with Kraft, all right? So I actually used this library in Castle Game Engine, in one of the Castle Game Engine demos. The demo is called Not Quake, because it's a Quake developed in one day, actually. It was a game jam. I started with zero knowledge about how to integrate those two libraries. Well, I did have some knowledge about Castle Game Engine, all right, but that's it. And then in one day, actually, I managed to integrate Castle Game Engine with RNL, Real-Time Network Library, and get something like a Quake-free prototype. You will see it in a second. If you'd like to, you can actually go ahead and copy this URL and just download this game on your Windows or Linux machine. It runs on the actual server. It runs on the actual server right now. I want to show it, actually. So let's go ahead. It's just this. There are not so many interactive demos in this presentation. I could not resist to actually show this one. All right. So let's go ahead. Let's run the client. All right. That's my nick. That's a good nick for starters. All right. And that's one window of the game. Okay. It's done in one day. Remember. So that's why it looks like this. Okay. Nothing fancy, right? Yeah. But then let's run another instance of the client. Okay. And by the way, those two instances of the client, they do communicate, but they don't communicate on localhost here. They communicate using actual server running on the internet on my server. Yeah. It's also written in Pascal. It's also written using RNL, of course. Can I look at each other? Yeah, yeah. So in one window, I'm now walking using Castle Game Engine. In the other window, I see the result of this walking. And it works. It's all like synchronized. I think I can shoot this guy. Yeah, okay, I can shoot it. I can also use, So in one day, I implemented Quake and the Slack also because I can talk. Okay, not really, not really, but you get the point. It's actually possible, and it was tremendously fun, of course. And by the way, I'm going to leave one instance of this thing running. If you want to shoot me during this presentation, go ahead and do it. Okay. If you download the client, it will automatically connect to the server, the same server that I'm using. All right. More stuff from Benjamin Rousseau. PasVulkan. He's implementing, and this is, I think, his main project right now. He's implementing a game engine using Vulkan. Underneath, only Vulkan, which of course allows him to use some optimizations, use some performance specific to Vulkan. It's a prospective game engine. Those are his own words. So it's not a game engine yet, at least he doesn't consider it enough quality to call it that. But it's a framework. It's a framework, so it's a bit lower level than maybe you would expect from a game engine. And it supports a number of things. It's cross-platform, everywhere where Vulkan is at least. It can also work on Mac using some compatibility layer. It supports sprites, a very nice UI system. It's integrated with his other projects also, the Kraft and the PasGLTF to render GLTF models. It's all integrated there. It has a custom project manager, a bit like Castle Game Engine build tool, and that's what it looks like. Okay, so it's kind of it's all rendered natively in Vulkan. Yeah, I mean this whole window that's not. Those windows are inside, are all rendered using Vulkan. And there's a 3D model inside. And yeah, it's cool. It's cool if you're looking for a Vulkan dedicated game engine that maybe doesn't have an editor yet, but if you just want Vulkan, yeah, no, only Vulkan, that's it, that's good. Okay, and the third game engine that I want to talk about is Apus Game Engine, developed by Ivan Polyatov. It's an open source game engine, 3D and 2D, Delphi and Pascal. This goes for all the game engines that I've been presenting so far. A number of unique features, but it has a powerful 2D supports. Effect, like GPU particles, GUI system, like you can actually modify things at runtime and they work in a sensible way. It has a scripting like built into the engine, like in Quake and many other engines. It can be used as a framework in the sense that there are a lot of actual units providing various capabilities, and you don't have to use everything. You just use some of them. I'm actually incredibly interested how it compares to Skia, for example, because it is in kind of the same space, right? Two-dimensional, heavy on effects. So I'm very interested in how it compares to Skia, but I don't have a knowledge about Skia enough, actually, to make this judgment. Here's a short demo. Yeah? So it's a three-dimensional demo, a bunch of billboards. Here's a three-dimensional demo that displays a simple model for glTF file, and it has a shadow. Here's a three-dimensional models using glTF with skinning on GPU, and here's a model of galaxy or something, but something big, yeah? With a lot of particles. So this is a short demo of Apus Game Engine, okay? And it's actually been used to make production games, the games that people actually play and pay for, and then they like them, so, okay? So like Spectromancer, Astra Heroes, you can research it on the web. But basically, it's a practical game engine, yeah? It's actually used to make production applications. Yeah. The things in the development right now in Apus Game Engine is styling, using cascading style sheets. Again, like a narrative. Yeah. This also connects to some other things some other people have ideas about in Pascal. Okay, so Apus Game Engine is also exploring this avenue. There's a work about supporting more 3D formats using async library, and there's a work on making the cross-platform, I guess, more easy to use TCP server integrated in Apus Game Engine, so you can easily use it in games. For details about this, yeah, go ahead and check out the Apus Game Engine. Talk to the author, he's amazing. All right, and that's the last part of our talk, important features of 3D visualization engines. So if my talk was not enough and you'd like to research and choose some game engine or just visualization engine on your own, or if, yeah, God's sakes, you want to create your own, here I'm going to give you like some lessons learned, what I think is really important when developing those things or when choosing those things. Can I get an estimate? How much time do I have still to talk? So, the things that matter, and this is the slide that connects to my, I want 10 hours. Can I have 10 hours? Oh, yeah. So the standards matter, okay? So this is the thing that why I'm also involved in this development of glTF and X3D, and why I worry so much that, you know, we should all use them, because it really, when you use the standardized model format, everything is easy, because there's a lot of job done for you, basically, by other people. So if you're looking about what model format to support in your game engine, look at two things. What is actually used by others? Yeah, the standard has to be practical. The standard has to be something adopted by other people. And the second thing is the standard, is this model format designed in a way that encourages others to enter the ecosystem. There are, for example, proprietary model formats, like the one at never mind, it's called FBX. It's proprietary, so not never mind, yeah. It's a proprietary model format. It doesn't encourage other people to enter the same field, and everybody is moving away from FBX to something else, like glTF. So use open formats, because then you're in good company, you're in a company that grows. You're in an ecosystem that is getting more and more expanded by more and more applications. And the very short summary of this slide, use glTF, that's great. All right. And also observe what X3D and USD are doing. In X3D, we're doing some cool stuff. USD is also doing some cool stuff. An example of those applications, this ecosystem around you, what does it mean? Well, it means, for example, Blender. Yeah? So I don't implement Blender. Well, I cannot, nobody can. Blender exists, and Blender can export models to glTF with kind of a perfect quality around how they handle some details. Kronos is actually sponsoring this development. Cool, so I'm using it. Yeah? Blender to glTF works, and I'm happy to use it. Godot engine is also using it. Many other open source engines are also relying on it. And then Sketchfab integration. This is the benefit of, this is something that I actually got news about just before arriving, I mean, last weekend, yeah, it was just before this conference. So if you go to the Sketchfab website about what game engines are supported that can actually download Sketchfab models, like inside Castle Game Engine, we have this simple window where you can say, okay, I want to grab some model from Sketchfab. Actually, since we have 10 minutes, let me show it, okay? Let's do this. Something unique, all right? So how does it work? Okay, so the integration with Sketchfab, data info from Sketchfab. Now, anybody say any word, English. Anything goes. Oh yeah. So let me search for castles. And now I'm searching actually the Sketchfab website for models of a castle, for three-dimensional models of a castle. I can see what license they are, Creative Commons, something, something. What phase count is it, so basically how heavy they are to render. And yeah, I can also look at actually the thumbnails of them. Now I can choose any one of them. Oops. Let me speed it up this way. Sorry. Not exactly sure what happened. So let me choose some castle model, maybe this, castle on the hill, and I can say download and add it to the viewport. And no idea what happens. Oh, this one is actually kind of pretty, yeah? So this is the castle that we have downloaded from the Sketchfab, and yeah, you can just use basically the Sketchfab as a repository full of really high quality, actually, three-dimensional models that you can search and you can use them. Yeah? For example, I can duplicate this model so I can create multiple castles like this. So I could use it to actually design my three-dimensional world if I'm patient enough to search for everything I want to. So, and that's cool. And this is all open source. I mean, those models have Creative Commons something licenses. Most of them are compatible with the general open source definition. And wrapping up, yeah, so, and the Sketchfab added us to their webpage as an engine supported by Sketchfab that supports getting Sketchfab models, and I'm so happy that like we're in this very good company of well-known engines, much bigger than us, yeah? But then Castle Game Engine is the first game engine mentioned by Sketchfab, which is probably we should call the engine like AAAAA, just to be sure that we stay at the first place on this alphabetical list. Anyway, nice. Other things you should look for, so graphic effects. Graphic effects improve realism. So they make things look nicer. Graphic effects, they also improve like what happens on your screen. So it's basically not boring. So if you activate shadows or mirrors or bump mapping, those things are not just realistic. They also mean that when something small happens, like the lighting moves or the camera moves, then a lot of other things happen, yeah? Because when the lighting moves, then the shadows also move. And then the bump mapping shows you different surface look, yeah? So the graphic effects increase how well your scene looks like. And in particular, the physically based rendering is now standard, and in more particular, look in your engines, or the ones that you choose for shaders support. If you can write your own shaders in any shader programming language, that's a powerful thing, because shaders allow for incredible number of cool things to be made. Here I'm displaying water and shadow maps. Yeah. Physics engine, you saw this one, it's fun. Yeah. So use physics engine. Platforms. Selling games today is hard. I can tell it as a co-owner of our game company. It's hard market because there are a lot of people selling games. So you want your stuff to be cross-platform. And because this allows you to ship your game to a number of markets, like the Xbox market, the Windows, the Steam market, itch.io, and so on. The Google Play, that's more important. So use the cross-platform feature of your game engine to ship your game everywhere you can. And integration with Steam, Google Play, so on, is important here too. You're doing this for the long term, so of course, like the human things, I guess, are a factor too. Active community, developers, active developers this is the value of the project, yeah? Pretty much almost nothing else matters. If there's an active community and active developers making intelligent decisions, and everything else will work out. Anyway. Documentation, and of course I already mentioned the continuous integration and delivery. Yeah? You want to test your applications, you want to test your games. Games are natural, like generators of unexpected experiences. And you know what happens with unexpected in software, right? So you don't want bugs, games need testing, and the continuous integration delivery allows you to have easier testing because you can test every build you have, and it allows you to also ship like a hotfix for something really quickly. So use continuous integration delivery. You are probably the crowd that is already doing this, but in game development community, I feel it needs to be more emphasized. All right, graphic tools. There are a lot of graphic tools. Look for them in game engine, or look into making them in your own game engine, because they are important. Not only for graphic artists, though yes, also for graphic artists. A lot of things are much easier, or just they are only possible to just set up in a visual application like Blender, like Castle Game Engine editor. And yeah, you want to be integrated with them, because then the people can actually use your engine to design something pretty. And of course, the graphic tools are also helpful in a lot of cases for programmers, because you can actually debug a lot of things. Like our engine didn't have a game editor long time ago, When we started to introduce the editor, it was so cool because we have been able to find so much bugs. Because when you no longer write code, but you can just test some things by clicking around in the object inspector, you find you make so many new combinations that you will never be able to make in your code, and you discover how those combinations don't work, and then you fix them, and then you're perfect. Yeah? So graphic tool, using them is important, even if you're not a graphic designer. All right? That's it. Thank you very much. This is our website, my email. Talk to me whenever you want to, online or not online. Thank you very much for your time.